Hello. A few students asked about some questions on my open math. And then if more people show up, I'll go over more, but we'll start with these. The first two are from Chapter 9. School District. It observed that 35% of students in an element schools were classified as only children, no siblings. However, in a special program for talented and gifted students, 135 out of 332 students were only children. The school district administrator wants to know if the proportion of children is significantly different. The keyword is different here when you're talking about your alternative hypothesis. We know it's a p-test because they're giving us the proportion of students. And the proportion is 35% written as a decimal, so 0.35. We want to test that it's different. Different means it could be greater or less. It's just saying not equal to. Because of that, it's a two-tail. If it's greater than, it's 1. If it's less than, it's 1. We know that it's a p-test, so the null and alternative hypothesis would have a p. We know that we're testing not equal to. So less than, greater than would be out. It would be the not equal to, which is this one here. Your null hypothesis is always equal to your alternative. In this case, because it's different, it's not equal to. To find the z and the p-value, you go to Canvas. You can either use, you want to use your home screen. You don't want to use assignments. And then go down to, this is Chapter 9. And this was a hypothesis test. It's a hypothesis test for a proportion. So we use this one. So if it doesn't open for you, usually, now mine's opening, so it came here. If it didn't, then there'll be a link here that will open it for you. But this one's automatically opening. Enable editing. Make it a little smaller. And then we plug our values right here in the gray. Our alpha is 0.05 as a decimal. Sample size 135 out of 332, so 332. The number in the yes would be 135. The proportion comes right here from your, or here, it's from your null and alternative hypothesis, 0.35. And then our test statistics here, 2.16. And the p-value, it depends on if it's a left, a right, or a two-tail. And we said it was a two-tail test, so it's the 0.0305 there. And then to decide if you reject or you do not reject, if you go a little lower here, it will tell you. If the p-value is less than alpha, you reject. If it's greater than, you fail to reject. The p-value was 0.05 up here. And we said it was 0.03. 0.03 is less than 0.05. The p-value is less than alpha, so we reject. You reject the null hypothesis. You never reject alternative. It's either reject the null or fail to reject. Since we're rejecting the null hypothesis, the sample data supports the assertion that there's a different proportion of only children in the gifted program. So we reject the null hypothesis. So they just want the sample size is different. Another one, according to a study, I think this is also chapter 9. Yeah. But this one's a mean. So we wouldn't use this test. We need the mean test. You are conducting a study to see the mean doctor's salaries in thousands of dollars is significantly more than 86. A random sample of 28 doctors' salaries in thousands of dollars is shown below. Test the claim using 1% level of significance. So we will need back to chapter 9. This one's a hypothesis test for a mean. So we said it was mean. This would be mean. We're testing that it's significantly different than 86. So this would be mean equals, and this would be 86. Significantly more than. Because it says significantly more than, they would also accept less than or equal to. Most books and classes, it's only equal to, but less than or equal to is also the opposite of greater than, which is what we're testing. Because we're testing that it's significantly more than. This number here, 86, and the mean will always be the same. And then whatever this is the opposite. So it will either be equal to or less than or equal to. You can take either one. To find the test value and the critical value, we first need to find the mean of the data because they didn't give us the mean. So we have to find it. Let's see, maybe this will let me copy it. We'll see. I'm going to put it over here. Enable editing. Okay. Well, looks like it's all right. So then if we want to find the sample mean, we would put equals average and these values. There we go. Sample size, 28 doctors. Population mean, that comes from your hypothesis. It was 86. We have that. Standard deviation. They don't give us the standard deviation, so we will also have to find the standard deviation from our sample. Start to type. We want it, it's from the sample. So we highlight that. Highlight our numbers. And then alpha was 1% or 0.01 as a decimal. Here's the t-value, 0.505. For the critical value, I believe the critical value is over here. Yeah, here it is. And so here's our critical values. Now we were testing greater than. Greater than is a right tail, so it's 2.47266. Of course, they're going to round it to a 7. Here you want to put your, let's see, it's a right tail. We're testing greater than. And then our value is the critical number. .4. They're going to round it to 2.5. Yeah. So this is our critical value. This is our test statistic. Our test statistic is 5, so it's way over here. It's definitely above. So we would reject the null hypothesis. The correct summary would be, there's enough evidence to support the claim that the proportion of mean doctor's salaries is significantly more than 86. Because we rejected the null, we accepted the alternative, which was greater than. The next group is from Chapter 8. The average student loan debt, I think they're oh, maybe they're not. Here's a mean. The average student loan debt is reported to be $25,235. A student believes the debt is higher in her area. She takes a random sample of 100 college students in her area and determines the average number is $27,524 with a standard deviation of 6,000. Is there sufficient evidence to support the student's claim 5% level? Is it safe to assume N is less than or equal to 5% of all college students in the local area? Yes. Is N greater than or equal to 30? We have 100 students. Yes. Determine the null and alternative hypothesis. Enter correct symbols. Okay. Our mean is 25,000. So this would be mu equals the 25,235. This is the same value except whatever you're testing. The student believes it's higher in her area. So this would be greater than. To determine the test statistic and the p-value, use the table. This is a test for a mean. Okay. So our sample size was 100. The population mean comes from your hypothesis, 25235, 25235. The sample was 27,524 with a standard deviation of 6,000. Alpha 5%, 0.05. T-value 3.8. They wanted 2 decimal places, so 3.82. To find the p-value, we are testing greater than, so it's a right tail. So it's the second one, 0.0001. Since the p-value, 0.0001, is definitely less than alpha, we reject the null hypothesis. Because we're rejecting, there is sufficient evidence to support the claim that the student debt is higher. We rejected the null hypothesis and accepted the alternative. I guess these were all chapter 9. This one says to test the claim that the mean GPA of night students is smaller than 2.5 at a 10% significant level. Now, this one is a mean. I did one the other day that was a proportion because it said the proportion of students have over a certain grade. But this one is the mean grades is smaller than 2.5. And so we're testing less than 2.5. The opposite of less than is greater than or equal to. And that's why they're using that. You could also use equal to here. Because we're testing less than, it's a left tail. Based on a sample of 80 people, the sample mean was 2.47 with a standard deviation of 0.07. They want us to find the p-value. This one's mean. Yeah, we had mean, so we're good. Sample size 80. Population mean 2.5. Sample mean 2.47. And standard deviation 0.07. Alpha was 0.1 right here. We just needed the p-value. We said it was a left tail test right here. So it's 0.0001. Based on this, the p-value is less than the null hypothesis. Right there, 0.1. 0.0001 is less than 0.01. We reject the null hypothesis.